Hello, everyone. Good afternoon, and welcome to my graduate seminar. I am Harshad Kalyankar, and I'll be speaking Leading Edge Vortex Liftoff on Cranked Finite Wings. This has been my topic for the last 1.5 years only. So, thanks to my advisor, Dr. Vegnansky, and my committee members, Dr. Little and Dr. Zohar, um, Aerolab team member, Dr. Taubuch, and thank you to current and former colleagues of Aerolab and TFCL and Dr. Sarke's lab. And special mention to our machine shop guys, without whom we couldn't have done anything related to experimental techniques. Um, it's late in the afternoon, so I understand if you might fall asleep. So we can make this a more of an interactive session rather than me presenting the entire way and then you asking your questions. So welcome. If you have any questions, you can stop me. So we begin with understanding what is a leading edge vortex. So on a delta wing, particularly with sharp leading edge, when this delta wing is pitched at an angle, there is a flow separation right from the leading edge. Now the flow separation behaves like a shear layer, and hence it forms these Kelvin-Helmholtz vortices. A note to be made is these vortices are discrete in nature. Now these discrete vortices along the chord of the or along the streamwise direction, they roll up at a particular span and they form a vertical structure. These vertical structures develop and behave, and that's what we will be looking at today. Here is a plot of CL, that's the lift coefficient versus alpha. At low to moderate alpha, these these KH vortices roll up into vertical structures and progress. And when we go to a bit higher alpha, we reach a certain point wherein these vertical structures become large enough such that one structure occupies approximately the half span of the wing. Further, if we go higher, we reach a condition called as vortex bursting. Now, people who are new to the CL alpha plot, this region is where we experience stall of the aircraft, where we have no control over the aircraft and the control surfaces of the aircraft. So this region experiences something called as vortex bursting, wherein the traditional definition is the actual velocity of the particles in the vortex achieve stagnation. That is, their actual velocity go down to zero. So air molecules or particles just go everywhere. A lot of researchers have focused on this region and did some active flow control techniques to extend or to control this vortex bursting nature and extend this stall region to higher alpha. So you have a larger angle of attack for the flight envelope. One example I would like to give is from Margalit from 2005. Here they had a sharp leading edge delta wing with a front sweep angle of 60 degrees. And the results we'll be looking at are the PIV results over here at the vertical plane over here, approximately x over c of 0.6. The wing is pitched at an angle of almost 38 degrees. So you can see that's a very high angle of attack. In here, you will notice that as I had mentioned earlier, there are shear layers. So you can see the vorticity profile over here. This is one structure of a shear KH vortex. And you can see this is a negative vortex that is clockwise motion. And you see another discrete vortex over here for this particular phase angle of 0 degrees. So over here, you see like two discrete KH vortices. Now, as we progress in the phase, you can see that these two KH vortices, they kind of twist around each other. Now, if we see for 0 degrees, we see the streamlines over here. You can see two locations of the center of the vortex. And as you go in the phasal progression, you can see how these two vortices are rotating around each other and also interchanging vorticity. At some point, like over here at 270, you can see that the strength of the individual vortices have reduced. This could be because the vorticity in this plane may have convected streamwise downstream, so we are no longer recording it. But from here, you can see that there are discrete vortices which like go around each other and form this um, vertical structure on a delta wing, which we call as leading edge vortex. These were phase averaged PIV results. So so now what is the result when we introduce a crank? Now a crank is basically a location where we are changing the sweep angle. So here you see the leading edge sweep angle is 60 degrees and it's changed to 30 degrees. So this is the crank region, and it's usually the cranks are like very sharp change in angles, but here you can see there is a curvature to the change in the angle. When we look at the side view of the model, you can see that the model is pretty thick. So this is not a thin or a sharp leading edge model. Additionally, the leading edge curvature, or there is a non-zero leading edge radius to the model. So these factors, that is the thickness of the wing as well as non-zero leading edge radius, do affect how these leading edge vortices develop. And then on top of that, you add crank to the equation, so that affects the evolution of the leading edge vortex, which we will be focusing on. So here we will look at a particular angle of attack that is 14 degrees, and I'll mention later why we chose the 14 degrees. What you're looking at right now is an experimental technique called as surface oil flow visualization technique, wherein uh, we put a layer of oil, titanium dioxide, and kerosene, or a mixture of these three fluids on top or on the surface of the wing, and then we start the wind tunnel. So you can see how this mixture flows along the wings, and that shows us different structures that can occur on the wing. So at this angle of attack, we see that the fluid that is over here, which we call as the inner main wing, goes or has this rotationary motion or rotary motion, sorry, and is entrained and goes on the outer side of the wing. Over here, if we focus on this region, which we call as focus of separation, that has been extensively studied in the literature, it identifies as a location where the vortex lifts off from the surface. And you can see that surrounding this location or this structure, there are these curved streamlines, surface streamlines, that identifies the liquid or the fluid that is over here being entrained by this vortex liftoff process. And you can see a pretty nice boundary over here. I'm sorry? So over here, you cannot see the leading edge vortex that is being developed from approximately the root of the model that goes almost along the leading edge. Right. So you can see the curvature over here that identifies the footprint of this vortex liftoff. So when we look at this, we can make a 3D understanding of how this vortex may be lifting off at this crank, and this vortex has an anti-clockwise motion. Now, why is this vortex lifting off, particularly at this location? We have horizontal free stream identified by the yellow arrow. Now, this free stream velocity direction can be decomposed into two directions, chordwise and um, spanwise. For here, because of the sweep angle being 60 degrees, it is decomposed like this. And then when we go to the outer wing, where we have a smaller sweep angle, meaning we will have a stronger chordwise velocity and a relatively weaker spanwise velocity. Hence, we do have a spanwise adverse pressure gradient along the leading edge. And hence, the vortex that is being developed over the leading edge is overcoming this adverse pressure gradient, and hence lifts off at this or near the crank region. Right. The trajectory stability. So that's the implication of a crank, that we are kind of forcing the vortex or the vortex lift-off location. Further on the outer wing, you can see some interesting structures forming. The streamwise direction is towards the right, yet you see some reversal or flow reversal over in this region, and you can see some curvature over here. Now, if you see a flow curvature in this region and that region, that indicates that there should be a saddle point over here, wherein part of the flow comes and re-energizes the vortex liftoff process, and part of the flow goes outward and joins the tip vortex. Now, the vortex that lifts off, like this 3D vortex, in order to have such kind of flow reversal on the outer wing, the trajectory of this vortex liftoff is hypothesized to be marked by this yellow line with the anti-clockwise rotation, which will impose the flow reversal on the outer wing. Okay. Now we will elaborate more on this later on. But when we were looking at a different wing, we did see that a long time exposure picture with smoke impinging on similar geometry wing revealed a bimodality of this vortex liftoff process, wherein you can see that part of the smoke is going streamwise and part of the smoke goes spanwise and then streamwise process. So we hypothesize that even on this model, we may see a bimodality of this vortex liftoff. Now, why, like all of this was happening at alpha 14 degrees, why did we choose this particular angle of attack? Because if we go a little bit low at a lower angle of attack, that is 12 degrees, we do not see any vortex liftoff process. We just see a slight span-wise outboard curvature of these streamlines for pretty attached flow. Okay, and on the lift versus pitching moment curve, this is the region that we are highlighting. This data point is for alpha 12 degrees and that data point is for 14 degrees. What is different about this range? You have pitch up motion or pitch up moment in this region, pitch up moment in this region, but in this region you have this slight kink where you have a pitch down or a nose down motion of the airfoil. So there is something happening with respect to this vortex liftoff process that initiates this nose down behavior in this particular wing. Is this behavior limited to this particular model that we investigated? No. Similar surface oil flow visualization was seen on blended wing body design that was tested at NASA Langley in 2013. You can see that from the oil flow surface streamlines that there is a vortex liftoff here, and due to the outer wing being larger, you can see some evolution of the outer leading edge vortex structure as well. So this that signifies the importance of this particular behavior that we are investigating. Okay. Now, if we continue looking at the same lift versus pitch moment plot, we are in this region wherein this the black curve with circle markers was the one that we looked at earlier. Now, just on the outer wing, just outside of the crank at this red mark region, if we have a slot which is 50,000 thick, 50,000 inch thick, or 1.27 millimeters thick, so very tiny slot, that can significantly impact how the pitch behaves. All right, at this particular alpha range. But prior to that, or at smaller alpha, you do not see any difference with or without that slot. So this liftoff process that we were looking at earlier, if we introduce a slot around that location, we can get either pitch down, which is signified by negative pitch values, or nose up, which is signified by positive pitch values. Now, from prior experiments, we know that when we introduce a slot, which we do over here for this NACA 2L airfoil, there is a leading edge vortex being developed over the entire wing that is represented by this blue region over here, these are the results of pressure sensitive paint. So the blue region shows us negative or low pressure region. And when we have slots on the wing, we do see that this large vertical development is broken down into different leading edge vortices. Okay, so considering or getting taking inspiration from this work, if we introduce a slot here, we see that we are effectively affecting how the leading edge vortex was being developed on the outer part of the wing, and hence we either get a nose up or a nose down pitch moment. Now at this slot, if we introduce a sweeping jet actuator, which is basically a pneumatic jet, but it sweeps and we orient it vertical, so it kind of acts like a fluidic fence. So it affects how the span-wise flow is flowing over the outer wing. And if we actuate this particular actuator, we do see that this entire nose down pitch behavior was negated, and we get this red curve. So we get just the pitch up behavior with this zigzag pattern that was earlier for the black circle, but just at a different alpha angle. And at that same location, if we introduce a steady supersonic jet, which was designed for 1.5 Mach number, but inclined towards the inboard of the wing or the inner part of the wing, we completely eliminate this zigzag behavior. So you see the blue curve doesn't have this zigzag behavior. So via these pitch behavior data points, we understand that there is something happening with this vortex liftoff that we are able to affect with the use of these actuators, but we don't know what we are doing. We are able to solve the problem without understanding what we are doing. Now, as I mentioned earlier, that if we go at lower angles of attack, the existence of the slot is irrelevant because the pitch is not affected by the existence of the slot. But with the actuation at that slot, we can get a nose up pitch moment, or if we do the supersonic jet actuation inboard, we get a negative pitch moment. So if we are in these alpha range, we can have on-demand pitch up or pitch down motion of the aircraft, which is pretty significant if you're flying an autonomous UCAV. Now, this behavior that we investigated is not limited to this particular model as well. If we look at a generic delta wing model, that which is the ICE model that was being studied at the Air Force Academy, you can notice for the no forcing case that is identified by the solid pink line, you can notice this zigzag behavior. More importantly, if you look at the simulated data, which is identified by the broken line, the simulation doesn't really capture this physics. So our lack in understanding of what's happening over there implies that we are not able to simulate that behavior, and that's pretty significant. Another example is if you look at Elmil Gui et al. In 2017, they did a multi-sweep wing or analysis on a multi-sweep wing, and you can see that the bimodality that we were talking about earlier is not quite noticed or not quite observed over here, right? So this is the simulated data. I'm sorry. These are the simulated results, and the bimodality that we were talking earlier is not quite identified here. So there is this lack of understanding between what's happening experimentally and what's being simulated that needs to be explored by better understanding the physics. So that that signifies our current work. If we are doing another quantitative experimental technique called as particle image velocimetry, we are using a laser which is vertically oriented at this location, so just outside of the crank. And the laser, there's a process and it gives us velocity magnitudes and direction that are plotted over here. So in this, we have the in-plane velocity magnitude and the streamlines overlaid on top. So for alpha 12 degrees baseline, you see that the flow is pretty much attached. We have a strong acceleration of the flow at the nose of the wing. When we look at the Z velocity, we see that this high acceleration gives us low pressure region, so negative Z velocity. And towards the trailing edge, we have weak positive outboard flow that is identified by the surface streamlines over here. right? But apart from that, we have pretty attached flow at this particular location, at this particular angle of attack. Now, when we increase the angle of attack to 14 degrees, where we notice this vortex liftoff process, we see a huge recirculation region. And to complement that recirculating region for the W velocity, we have this strong outboard flow that is represented by this entrained flow from the inner wing to the outer wing. At the nose, we have, over here, we do not have as strong of a flow acceleration. And in here, we have negative flow velocity that is marked by the incoming or the flow over here moving inboard to re-energize this vertical core over here. And then there is this tiny structure in red, which identifies a new vortex being developed on the outer side of the, I'm sorry, on the outboard of this PIV plane. So basically a new vortex for the outer wing. With AFC, that is with this supersonic jet, we were able to completely almost get rid of that recirculating region and reinstate that flow acceleration that was missing over here. To complement it, the outboard flow that was dominant in the rear part of the wing is eliminated. And from the oil flow, you can see that the jet is located, or like the actuator is located over here, and the jet comes out in this direction. The PIV laser plane is here. So this, the jet is highlighted over here in dark blue region. There are tiny recirculating region of the jet, which is, even my pointer is a bit difficult to hold, over here and over here, which is identified by this tiny red region. And then we have the leading edge vortex for the outer wing. So the jet that kind of intersects with this leading edge vortex liftoff process, hence restricting this process to a smaller region over here. And you can see the inboard streak line, instead of curving outboard like how it was, it just goes span-wise streamwise downstream. Sorry. Right. So it's a steady supersonic jet. It's incoming in this direction. So it's blowing towards the inner wing. Right. Over the upper surface of the wing. So it kind of intersects with the liftoff process. Right. So moving on, these were the ensemble average risk. So it was designed for Mach 1.5. It's happening really, we are not quite sure. Right. If I remember correctly, the nose, the throat diameter was 50 thousandths in thickness, in diameter, 50 thousandths inches. So moving on. So earlier, what we have been looking at was the ensemble average result. So we have a question: if there is some unsteadiness in this process, and one way of looking at unsteadiness is like doing high-speed PIV or something, if you have the equipments available, or looking at something, a mathematical technique called as snapshot POD, which is proper orthogonal decomposition. So here, what we do is essentially we take the velocity, which is both spatial and temporal, or which has both spatial and temporal dependence, and we break it down such that we look at the spatial development as is and temporal development as a different entity. How do we do that? We create a correlation matrix using the velocity and the transpose of the velocity, and we calculate the eigenvalues and the eigenvectors of this matrix. The eigenvalues are mentioned over here as the percentage turbulent kinetic energy, and the eigenvectors are decomposed into spatial modes and temporal coefficients by more math that I don't want to go into here. The eigenvalues are rearranged as, or from its largest to smallest. So you can see that the first mode, which has, first mode has the highest energy content, which is about 13%, and then it decreases. And in the first 10 modes, you have about 40 to 50% of the energy being captured. This first eigenvalue, the spatial mode or the corresponding spatial mode, is highlighted over here. You can see that this, comparing it to the ensemble average baseline result, this highlights the unsteadiness of the dividing streamline. And then when we look at the higher spatial modes, you can see there are the opposite signed structures here, which indicate there is some convection happening, or some, I'm sorry, highlight the convective structures that are developing in the downstream direction. So through this process, we are like able to differentiate between the spatial development, and then for the temporal aspect, we can look at this plot, which shows us the temporal coefficient for the spatial mode 1, which is over here, versus the temporal coefficient for the spatial mode 2 over here. What's the significance of this particular plot? We take this, which like each data point over here identifies each snapshot of the experiment. And then the red dot is the mean of in both the direction or on both the axes, which is pretty close to 0, 0. Then if we take a small sliver of this piece of data and average the data points over there, we can kind of get phase averaged results. So if you look at this particular data or this particular wedge of the data, we can see that at theta equals to 0, we have this recirculating region, but then relatively thinner recirculating region. As we process and this flow acceleration, which was not there for the ensemble average results. Now, if we look at another sliver of the data, we get the phase progression, wherein we have the enlargement of this recirculating region. And then we progress along and we see that this recirculating region enhances, and then we have some saddle point and a nodal point of attachment in the downstream of this recirculating region. And finally, there is a structure that sheds from the recirculating region, and the size of the region becomes smaller again. So you see that although we didn't do time resolved PIV, we are to a certain extent able to get some kind of understanding of some periodicity, some periodic behavior that may exist in the flow. All these are reconstruction of first 10 modes. Right. So I was able to capture about 40 to 50% of the energy of the turbulent kinetic energy that was in the flow. About 1,000 samples. That depends on how the data is distributed in there. You could approximate about 100 or so in individual averages. But I can get that exact number later if you're interested. Now, we can look at the phase development of the in-phase velocity, which you looked at earlier, and the out-of-plane velocity, that's the W velocity here. Now, in here, you see that for theta equals to 0, where we had a very thin recirculating region, there is activity in the rear of the wing. And you can see the leading edge vortex for the outer wing that is over here, but there is not much interaction between these two structures. But when you progress in the phase, you can see that the leading edge vortex becomes stronger and stronger, grows in size, and also the zero location for this outboard velocity goes upstream and upstream, and there is interaction between these two structures. And that gives this periodic or unsteady behavior, which we found out to be periodic as well. With actuation, the recirculating region is almost negligible for the in-phase velocity. And for the out-of-plane velocity, you can see that in the rear, there is some unsteadiness, but pretty low in magnitude as compared to the baseline flow that existed earlier. The most significant observation here is this leading edge vortex that is being developed on the outer wing is almost consistent in its size and strength, meaning that the interaction between this structure and what was happening downstream of the jet was effectively eliminated by introduction of this steady jet. That you can also verify from the oil flow, that earlier we had these entrained streamlines that are not curved right now. So we see from the ensemble averaged and non-time resolved data that there is some periodicity in the flow that we would like to investigate more, but because of lack of high-speed PIV, we did some non-traditional approaches. So in here, what we looked at was a different wing with the similar geometry. We selected this wing because this is almost same thickness, or the wing is almost same thickness as compared to the earlier wing where the thickness varied along the span, and we had troubles with the laser reflection and everything. In here, we do not have those troubles. There is still non-zero leading edge radius. So that does impact the leading edge vortex development. Also, as you can see, there's a big hole in the middle. So that does influence how the flow behaves as well. So we are looking at this region, and this is a picture from earlier where we had a long time exposure of the smoke, and that showed the bimodality of the flow over the swing. Now, when we look at this region with smoke and a high-speed camera recording at 1200 hertz, you can see some flow structures that are developing. I'll let you just observe this. So these structures definitely catch our eye. And when we look at individual frames, so you can see the time development in the third order of magnitude. You can see that it impinges at closer to the crank. The smoke impinges closer to the crank, and it develops on the outer wing. This development creates some kind of roller structures that can be identified over here. And as time progresses, these structures move over the outer wing. And at some point, you can see the two structures. I'm sorry, a second structure that is coming. So you can see the periodicity of these structures. Now, these, from a different vantage point, resemble something that looks like a Kelvin-Helmholtz type vortices. Now, these were forced Kelvin KH vortices on free shear layer, forced shear layer in a 2D mixing layer. Whereas in here, you can see that these vortices have an axial flow due to the entrained fluid from the inner part of the wing. So although like from images, it looks similar to 2D KH vortices, we do have three-dimensionality in the flow. So that does complicate our physics in here. So we we see some existence of periodic structure that are similar to 2D KH vortices. By some hand calculations, we were able to calculate the Schroll number, which was about 0.04, which agrees with the theoretical maximum of the spatial amplification, which was mentioned in Mihalke's paper. Then the entrained flow from the inner wing provides the axial flow to these vortices, and like adding to the dimensionality of its evolution. And these eddies might interact with each other and impose the flow that is being developed on this outer wing. So that complicates our physics as well. Now, the unconventional technique that we used was, we did the POD approach that we mentioned earlier, that I mentioned earlier, on these smoke flow images. So we were doing POD on pixel intensities, smoke pixel intensities in these images. And these are the results. The top row is the result closest to the wing. And as you progress in the row, we are going further away from the wing. And you can see that the development of this flow is three-dimensional in nature. There are two branches, the one going streamwise and one going spanwise. And for the top row, at least, you can see the evolution of the structure over the outer wing. And then when you go further away from the surface, you see that the streamwise still has some variation and is highlighted over here, whereas the span-wise is almost gone. So that shows the three-dimensional development of this process. Now, when we look at vertical planes, the one very close to the leading edge, we see this. So in here, we are going from near the crank uh, to the wing tip. For the first station, which is very close to the leading edge, uh, we like barely see any changes. So we see almost pseudo steady flow. As we go further away from the leading edge, we see that there is some structure, some shedding that is happening on the outer wing in the spanwise direction. As we go further along, in addition to this spanwise shedding, we see that there is this vertical oscillation as well. The vertical oscillation as well. And the vertical oscillation enhances as we go further away from the leading edge. So like to summarize these results, what we see are oscillations in two directions, vertical oscillations and this horizontal shedding, kind of agreeing with the bimodality hypothesis that we had earlier of the vortex liftoff process and how it affects the flow on the outer wing. So this liftoff process is an unsteady, possibly bimodal process with periodic shedding on the outer wing of these KH eddies. And if we look into, like if we do the phase analysis, we can see that there potentially might be a interdependence of how these KH eddies are being shedded in the horizontal orientation versus how these structures are oscillating in the vertical direction. So that interdependency needs to be investigated as well. Now, we have these time-resolved smoke images, so might as well do some spectra on it. So we choose a couple of locations, and when we do some spectra at these locations, we see two peaks, one in the neighborhood of 60 to 70 hertz and one in the neighborhood of 100 hertz. When we did hot wire measurements, we do see those two peaks as well. When we are closer to the surface, we see peaks in the range of 100 hertz. And when we are away from the surface, we see peaks in the range of 50 to 70 hertz. So this suggests that although the smoke flow visualization and the POD on the smoke flow, although these are all qualitative experimental techniques, it connects well with some of the other quantitative experimental techniques results that we did. So the interpretation that we have from the smoke flow do lead us somewhere. To summarize the work, flow over cranked wing geometries were investigated. Leading edge vortex liftoff location was fixed near the crank and highlights the entrainment of the flow in the baseline, which was eliminated when we have this one actuator, and both of these have huge impact on how the pitch moment behaves. Then there were some periodic KH eddies that were observed on the outer wing. Now these eddies might impose an initial condition on the new leading edge vortex that is being developed on the outer wing. And these interactions may have some interdependency that we will have to investigate more. So this research, rather than answering questions, raises a lot more questions. Some of them are listed over here. Is there a single frequency or multiple frequencies at play during the leading edge vortex development? Needs to be investigated. The vortex that is being lifted off, has it already undergone vortex breakdown? Because according to literature, vortex breakdown is usually happening at very high angles of attack, but we are in the moderate angles of attack range. So we are not quite sure, and we need to do more experiments to figure out if the breakdown has already occurred. Apart from KH instability, are there any other instabilities at play? Because if there is vortex breakdown being considered, then there are other instabilities like helical mode instability that are at play. Are they responsible over here or not? We are not sure. This periodic structures and the development of the periodic structures that we saw do create buffeting on the wing, which we could physically see during the experiment. With actuation, that buffeting was eliminated because the periodicity was eliminated. So we need to investigate whether these instabilities, how do these instabilities result in the buffeting behavior, and what does the actuation exactly do in order to reduce the buffeting. So I thank you for your attention, and if you have any questions, I'm open for it.
Thank you.